Let's take a look at Chapter 10. Chapter 10 is about how to evaluate future cash flows and within capital budgeting. So some of the topics we'll talk about is the vocabulary of capital budgeting, what that means, a whole bunch of acronyms here. We'll go through and talk about those and go from there. So where we're at in this chart is right in the middle here. NPV, that stands for the net present value. This means a project. So we look at the project's cash flows, and those cash flows are, obviously impact today and future years. And net present value is what's the present value of all future cash flows from a project minus its initial cost. Okay. Now, what goes into the R down here? Well, the R is basically what's the risk adjusted cost of capital with the project. So you start with the WACC, and you would adjust the WACC for any risk of this project. If it's riskier, we should kind of go with a higher number. If it's not risky, we would go with a lower number. And what also impacts the R is with the return is market rate of interest, market risk aversion. If we're in a booming economy, people take on more risk. In recession, not as much risk. What's the debt to equity capacity of the project, and what's the risk of the project itself? So all those things go into that little R number right there, which is the return, the required return on that particular project. So present value of all future cash flows minus initial cost equals NPV. So what's capital budgeting? The analysis of potential projects. Very long-term decisions involve large expenditures, very important to a firm's future. And they can't be undone easily. That's the challenging part with this is once you begin these, you buy these or you invest in these, you really can't undo these. So you need to make sure, are we doing the right thing? Will this work out the way we want it to? So I need to estimate cash flows both in and out. And the inflows are basically the return on a project, and the cash flow is the initial purchase of the project or investment in the project. And of course, we have the risk, and the R is the WACC of the project, and we evaluate the cash flows. So steps or capital budgeting project categories, it could be a replacement. Machinery is worn out. It's that machinery is building something that's very profitable, a product line that's doing very well for us. So obviously we want to replace machinery to continue to make that product. Sometimes though, maybe technology gets better, and we realize if we were to buy new machinery with better technology, we would actually save money. We would have less labor, less waste, and so on, gain efficiency. So even if existing machinery works fine, we might become aware that newer machinery is just simply better. We could expand, adding capacity to a factory, launching new product lines, getting into new markets. That's kind of covers 3 and 4. We can actually contract. We can say, well, maybe we need to spin off something, or a product line's not profitable anymore, so we're going to get rid of it. Projects that deal with safety, environmental issues. Quite often those are, if you don't do this, we're going to fine you, right? Something like that. There'll be a penalty to pay if we don't do the project. Mergers and others. So those are the big ones that you might think through. So projects can either be independent or mutually exclusive. If they're independent, that means the cash flow of one project is not affected by other projects. Mutually exclusive means the cash flow of one project could be adversely impacted by the acceptance of another. So we had to look at it from those two lenses. Is the project independent, or is it mutually exclusive? So independent would just be, if I do this, nothing else is affected. Other product lines are not negatively or positively impacted. If it's mutually exclusive, doing one thing negatively impacts another. So an example I like to use in Sioux Falls, there's one Home Depot. If Home Depot were to build another location in Sioux Falls, it's safe to say that the sales at the existing Home Depot would go down, so we'd have to take that into account if we build a new store. So just something like that would be mutually exclusive. Then give us some examples using two different projects, Project L and Project S. L stands for long, so kind of just think the bigger cash flows for L are in the future. They're in years 2 and 3. And then for Project S, we'll call it short, the biggest cash flow happens right away in year 1, then goes down. Both of them have a $100 initial investment. Both have a WACC of 10%. So what is the NPV, the net present value? So think of the words net and then present value. So what I'm doing is I'm taking the present value of future cash flows. So 10 at 1 year at 10% is 909. 62 years at 10% is 49.59. 80 at 3 years at 10% is 60.11. And I net those against the initial cost, and it's positive. It's 1879 for L and 1998 for S. That means I'm good. As long as the NPV number is above 0, it's positive, I would generally be inclined to say, yes, I'll do the project. And it also tells me that's the value I'm adding to my company over the next 3 years. So imagine that was a $100 million investment. That tells me that this project will return close to $19 million of value over the next 3 years of the project. Okay. So the rationale, as I mentioned, is as long as present values are greater than the cost, I would be most likely to say, yes, I would take on this project. So the NPV being above 0 is one of the main things to think about. And then I have to choose between mutually exclusive projects on the basis of higher NPV, which adds the most value. So going back to here, let's just say that L and S are mutually exclusive. I can only do one. Maybe they both are investments to solve the same problem or to do the same thing, but I've got two possible cash flow patterns based on how I work my investment. Well, clearly I would choose S, right? Now, if they're independent and I could afford both projects, I would say, sure, let's do both. But if they're mutually exclusive and I can do one or the other, I would choose S. Okay, so that's kind of what they tell us right here. I just told you the same thing as this. Okay, so then the next method that we use called IRR, which is the internal rate of return. IRR is the discount rate that forces the present value of cash inflows to be the same as cost. So whatever rate returns the NPV to 0 is the IRR. So basically, we've got our cash flow today, which is the cost of the project, and we've got our future positive cash flows with the project. And so this is the formula for it right here. That looks complicated, but I promise you it's not that bad. So we're taking the cash flows to the power of time divided by a 1 plus R to the power of time equals NPV. Now Excel has a formula that does all these for us. So Excel has a formula. Oh, this is the NPV formula. But Excel has a formula for NPV and IRR, and we'll use those when we do I'll do the weekly WebEx, and I'll show you how to do that. Okay, so IRR for a project is whatever return forces NPV to be 0. It's very similar to what I call the YTM on a bond, the yield to maturity from the bond chapter. It really works the same way. So in this example, IRR of 18 for L and 23.56 for project S force NPV to be 0. And that's good news, because remember that my cost of capital for this example they gave us was 10%. And so the decision factor is, as long as my return is above the WACC, I would generally say yes. So if I could only choose one project, I would choose S because it has the highest return. If I could afford both or independent of each other, I would say yes to both. They will both add value to my company. Okay. And so IRR and YTM are the same thing. The same math goes into calculating both. So yield to maturity is the return on a bond. If I buy a bond and I get a whole bunch of future cash flows from that bond, that's my yield to maturity. The project is no different. I invest in the project, I receive future cash flows. That's my return. So either way, it works the same way. So you can kind of recall YTM, it works the same way. So the nice thing about Excel is it gives us a formula to do this for us. It's called the rate formula. And there's also one called IRR. So they each give us the same answer. Very easy to use. I'm going to show you how to do that in the weekly WebEx. So I've already mentioned the rationale. Again, as long as our IRR is above the required cost of capital, we're good to go. We can say yes to the project. Okay. And I've already kind of mentioned this one too. Okay, so there's another one called MIRR, Modified Internal Rate of Return. And this one changes the assumptions from IRR just a little bit. IRR uses an assumption that says future cash flows from a project are reinvested at the IRR rate, which is not necessarily the way it really works. So MIRR says, well, actually, no, let's take a look at future cash flows being reinvested at the company's WACC, which is much more realistic. So IRR works, but it has an assumption built into it that's probably not super realistic. So MIRR is a way to fix that. And now we're going to use a WACC, the WACC amount, to come up with what's called the terminal value of cash flow. So terminal value means the ending value of a cash flow. So we're going to look at it from this perspective. And again, I can use this MIRR formula that Excel has to make it easier for me. And so you can see here that my required return is 10%. In year one, I'm investing $100. Then I get positive of 10, 60, and 80. And my MIRR then in Excel will give me the answer. And the way that works on a timeline approach is I do the terminal value, which means I'm compounding. So if you recall from the present value of money chapter, the time value of money chapter, compounding means I'm doing future value. So I take all of my cash flows and I take them to the third year, which is the terminal year, the end year, and I get the terminal value of my cash flows is 158.1. And then I bring that down to present value at a rate, and that gives me my IRR, my MIRR. So I take the 158.1 divided by 1 plus the MIRR, and I get 16.5%. Okay. Then another one that we can use is called profitability index, or the PI, the present value of future cash flows divided by initial cost. Measures bang for the buck. The higher, the better. Okay, so we'll go back to a project where we're going to get all the future values of it, and we get all the present value of future cash flows, I should say. For this one's 118.79. I take that 118.79 and I divide it by the initial cost, and I get a PI of 1.1998. And again, the higher that is, basically the more valuable the project is, the better the project is. And payback is a measurement of how quickly will we require the initial cost. How long does it take to get our money back would be another way to think about it. It's a pretty simple one. There's no magic Excel formula to do it. You have to build kind of what I call a timeline. So in this one, we're going back to project L, and we had the initial $100 investment, then 10, 60, and 80. And so we run what we call the cumulative cash flows. So we take the initial cost and we deduct from that future positives. So after year one, I have a negative 90. Then after year two, I've got a negative 30. Then when I go from years 2 to 3, I go from negative 30 to positive 50 because it's $80 cash flow. So I know I go positive between years 2 and 3. So I know the answer is 2 point something. Obviously, you can see the 2.4 right there. So I go 2 plus 30 divided by 80. And I get 2.375 years, or rounded to be 2.4 years. Do the same thing for Project S. Project S has that big payback right away in year one. So its payback is shorter. It's 1.6 years. There's good and bad about the payback. The strength is it kind of measures liquidity, right? The shorter the payback, the more liquid the project. Very easy to calculate and understand. However, there's nothing here about the time value of money. Not one thing in here deals with time value of money. Ignores cash flows that occur after the payback period. So it just kind of stops once we get to the payback calculation. It never takes into account cash flows that happen after payback. And it also says here there's no specification of acceptable payback. Okay, so there's really no measurement of what's a good amount. Like we have rules of thumb to follow for NPV, IRR, and MIRR. There really isn't one for payback, is what they mean. So we can fix one of the problems by using discontinued payback. That now brings in the time value of money. So now what we do is we take the initial cash flows and we take each one and we bring in the time value of money, all future cash flows. So $10 at 1 year, 10% is 909. 62 years, 10%, 49, 59, and so on. We build the cumulative based on that. So because we're using time value of money, the payback will be a little bit longer. Instead of 2.4, now it's 2.7. Then what they call normal versus non-normal cash flows for a project. The vast majority of projects have one change in sign. You have initial investment, money you spend to invest in the project. Then you receive a series of positive cash flows. But you can also have what they call a non-normal cash flow. There's going to be two or more changes in sign, which might mean at the very end there's going to be a negative. Maybe we have to reclaim something like decommission a power plant, put a strip mine back together again after, put the land back together again after doing the mining, things like that. So there's several patterns. There's no right or wrong to it, but normal just basically says there's one change in signs. This is the most frequent one that we're going to see in our homework is this first one. But you can have ones that are normal like this one where you have a few years of negatives. It's a really long-term project. To build it will take a couple of years. Then even once it's built, it'll take a few years for positive cash flows to happen. That's not unusual. And then down here, we got pluses, then a bunch of minuses. Non-normal just means there's two changes of signs. There's no right or wrong to the pattern. It's just that's very common. Then economic life versus physical life. It says here, consider another project with a 3-year life. If terminated prior to year 3, the machinery will have positive salvage value. Should always operate for the full physical life. Well, the answer might be no. It might be, well, maybe we pull the plug earlier to maximize cash flows. And so in this example, here's my cash flows and here's my salvage value for the equipment that I purchased. And you can see the salvage value goes down over time, as do the cash flows. That makes sense. And this tells me what the cash flows are under each alternative. Basically, when do I pull the plug? If I don't terminate and I run the project for 3 years, if I terminate after 2 years, if I terminate after 1 year, and then I do my NPV based on those three. These three alternatives here. Full operations, 2 years or 1 year. Here's my NPVs. Well, if I keep the project going for 3 years, I actually lose money. If I pull the plug after 2 years, I make 215. If I pull the plug after 1 year, I lose 273. So obviously what this says is after year 2, I pull the plug because I get this nice big salvage value over here. So what we're saying here in this example is I'd pull the plug after 2 years. Okay, so engineering life does not always equal economic life. Okay, so two different things. So in finance, we're trying to maximize the value of the firm, and what I would say is after year 2, let's start over. Let's start over. Okay, so that's how I do that. So pretty straightforward stuff in this chapter. Hopefully you'll find it a little bit easier than some of the previous chapters. As always, if you have questions, let me know. And then when I do the weekly WebEx recording for this chapter, I'll walk you through how to use Excel to calculate NPV, IRR, and MIRR.